Hey everybody, Mr. Judson here. So we're heading into Chapter 8, which will be our last chapter that we look at. I want you guys to know ahead of time that this, for some reason, Central Washington thinks this chapter is really important. There's always a lot of questions that come from this chapter. So real important that we make sure we get the ideas. Real important if we aren't sure about stuff, we ask questions, either through the office hours or just send me an email. We're going to start off with reviewing just things that we've learned in the past, different types of integration problems. But the rest of the chapter is based on what if we get an integral that we can't solve? It doesn't fit one of our situations. We can't do substitution. I don't see this situation where I can set up an arc sine or an arc secant or arc tangent, something like that. So they're going to be a little more difficult, but at the same time, it's one of those things that if we're on top of it and we're really paying attention and working at it, then it tends to not be too bad. Here we go. Let's take a look. So at the start of Chapter 8, there's two important things that we should see here in our book. First of all, on page 520, these are all of our basic integration formulas. Okay, think back to our formula exam. We should know all these. Okay, this is the stuff that we talked about in this chapter. And over here, they're giving us kind of some procedures or some strategies for getting through integrals. First of all, if we see something like this, we could always consider, multiplying it out, expanding it. Whenever we see a fraction, we can try and separate it into two different fractions. When I look at this looks like it might be an arctangent. This looks like I could do a u prime over u. And so there's, by separating two different fractions, we get some things that we know how to solve. We don't want to forget completing the square. We did this when we were dealing with the inverse trig functions. Anytime we have an exponent in the numerator that's larger or equal to the denominator, we want to do long division. And when you do that, this is the result that you would get. Consider adding or subtracting something and then dividing into two separate fractions. See, when you look at this denominator, the derivative of it is 2x plus 2. I don't see the plus 2, so I would add that, then turn around and subtract it, and then divide this into the two different fractions. So now this becomes a u prime over u, so it would be a natural log. This one right here, looks like that could be done with substitution. If we write this as x, move the 2 to the outside of the integral, and write this as x plus 1 to the negative 2 power. Don't forget our trig identities. We don't know how to integrate a cotangent squared or a tangent squared, but if we convert that over using a Pythagorean identity, this is something that we know. That's one of our trig formulas, or integration formulas. And then also this idea of multiplying top and bottom by the conjugate of one of our trig functions. We can create a Pythagorean identity that when you change that, then we can divide this into two different fractions, and maybe each of those could be integrated. This is one of our basic formulas. This one I can do through substitution. Okay, so they're just reminding us of things that we've already learned. All right, let's go ahead and try a problem now. All right, so these integrals that we're looking at for today, they're going to use all of our basic formulas, but there's going to be a little more to them. We're going to have to think our way through these. When I look at this one, my first thought is, it's a fraction. Can I do u prime over u? Well, that doesn't work. The derivative of e to the x is not 1. There's no square root. It could be an arc tangent, except I don't see something squared and I don't see the derivative of this up there. So I'm going to have to figure out some other way to do this problem. And so I'll kind of give you guys little hints here and there, but for this one we want to add or subtract the same thing from either the numerator or denominator. In this case, probably the numerator. Now, if I take the derivative of this and I want to see an e to the x up in the numerator, that means I need to get one there. And so our hint here would be to add e to the x and then subtract e to the x. So essentially I'm adding 0 to that numerator. So my integral would now look like this. 1 plus e to the x minus e to the x over 1 plus e to the x dx. You guys see if you can take it from there. All right, so I guess what I see here is if I was to divide this into two separate fractions, where I've got 1 plus e to the x over 1 plus e to the x, that whole thing would just equal 1. I could integrate that. And then minus e to the x over this denominator. And I feel like I could integrate that as well. So the integral of 1 plus e to the x over 1 plus e to the x dx minus the integral of e to the x over 1 plus e to the x dx. Now remember, as I go through this, if all of a sudden you kind of go, oh, now I think I know what to do, hit the pause button, work it out on your own, and then see if you get things right. So I would now look at this and say this is really the integral of 1 dx minus integral of e to the x over 1 plus e to the x dx. And I know the answer to this is just x. When I look at this, I see u prime over u. Derivative of this would just be e to the x. So that means that's minus a natural log absolute value of 1 plus e to the x and then plus c. There's your answer. If someone left the absolute value signs off of this, you could make the argument that I knew this was greater than 1, and so that's why. And it is, because e to the x, no matter what, this is going to be a positive value. So you do 1 plus something, you've got a positive result in there, and so we really don't need those absolute value signs. All right, let's try another one. So here's another integral that I would look at and say, okay, this looks a little harder than normal. I think once we get going on it, you kind of go, oh, well, that wasn't that bad. But one of the things I look for is, I always look to see, do I know the derivative of one part, and can I see that somewhere else? So I think to myself, okay, what's the derivative of a cotangent of x? Well, that's a negative cosecant squared of x. Now, I don't see that here, and I don't see myself making this equal that. So let's go over here. What's the derivative of a natural log of sine of x? Well, derivative of a natural log is u prime over u. So derivative of that would be a cosine of x. So derivative of this whole thing, cosine x over sine of x, that's what we have right here. And so when that happens, to me that says I want to do substitution and I want to let u equal this part right here. Okay, you guys go ahead and try it. All right, so if I let u equal natural log of a sine of x, then du is just going to be u prime over u. So sine of x, derivative of that would be a cosine of x, times the derivative of the angle, which is 1, and I just took the derivative of x. Remember, I want to see all that stuff in there. So if I rewrite this integral as natural log of a sine of x, this cotangent I'll write as cosine x over sine of x, and then dx. Then I could say, let's let u equal this part. Cosine x over sine x dx, that's just equal to du. And so the answer to that is u squared over 2 plus c. And so now I just got to substitute information back in. Got to be a little careful when I write this. I've got natural log of a sine of x and that whole thing squared over 2 plus c. You can move that 2 out in front and call it 1/2. But the thing I want to make sure of is I cannot bring this 2 down in front. See, if it was this piece squared, so the sine of x was being squared, then I could bring that 2 down in front. But it's the whole thing that's being squared. And so this does not apply to our properties of logs. This would be our final answer. All right, so when we look at this, in my mind I'm just thinking, okay, what is the integral of a tangent squared? That's not one of our basic formulas. I know that the integral of a secant squared equals a tangent, but that's not what this says. And so looking at this, I would say I'm kind of stuck. I don't really have a way to do this. And so what we need to do is we need to change this to something different. And I would use the Pythagorean identity. I see an exponent of 2. Remember that from last year? Anytime I see an exponent of 2 with a trig function, I'm thinking of those Pythagorean identities. So I know that a tangent squared plus 1 is equal to a secant squared of x. Remember, this is just my chicken scratch. So a tangent squared would be equal to a secant squared minus 1. So I want to change this right here. So I'm going to call this the integral of a secant squared of 2x minus 1 dx. You guys see if you can get it from there. All right, so the one thing I want to be careful of on this one is when I have an angle that's not just an x, I want to do a substitution and let u equal that angle right there. So let me divide this up into 2 different integrals. I've got a secant squared of 2x dx minus the integral of 1 dx. And so for this first one, I'm going to say off the side here, let's let u equal 2x. And so I take the derivative, that means, remember we do this implicitly. Derivative of u is 1, and I just took the derivative of u. Derivative of this is 2, and I just took the derivative of x. So I need to see a 2x right here. So I'll put 1/2 out in front to compensate for that. And now I've got it set up so I can do my substitution. So this will be 1/2 times the integral of a secant squared of u. 2 dx is equal to du. I already know the answer to this, so I'll just go ahead and write it down. Minus x plus c. Remember that negative sign, it really should be distributed to this, but I don't care if c is positive or negative. We'll add whatever it is. Okay? All right, so now the answer to this is just a tangent of u. So I've got 1/2 tangent u minus x plus c. And so I'll put my u value back in there. It was 2x. So my final answer is going to be 1/2 tangent of 2x minus x plus c. There it is. All right, so here's the next one. Got the integral of x plus 3 over the square root of 4 minus x squared dx. And so the moment I see a square root in the denominator, I'm thinking of those inverse trig functions. I'm subtracting the variable part, so that makes me think arc sine. But when I look at this, I need to have u prime. So if u equals x, I need to have the derivative of that, which is just 1, in the numerator. And I don't have that. I also think, okay, I've got something inside a square root. That's the same as something inside parentheses raised to an exponent. That always makes me think substitution. And so when I take the derivative of the inside, I would get a negative 2x. I could make that happen here, but what about the 3? So we got to figure out how to get through this. And I think the key to this one is separating this into 2 different trig functions. So I'd have the integral of x over, or separate into 2 different fractions, is what I meant to say. The square root of 4 minus x squared dx plus the integral of 3 over the square root of 4 minus x dx. So the moment I do that, I'm now thinking that I could probably solve this one using substitution and this one using the idea of an inverse trig function. You guys see if you can take it from there. All right, so I probably want to rewrite this one as 4 minus x squared raised to the negative 1/2 times x dx. And I'm going to go ahead and do substitution. I'll just keep on working with this. I'll come back and get this second piece in a minute here. So I'm going to let u equal what's on the inside. 4 minus x squared. So du would be a negative 2x, and I just took the derivative of x. So I need to see a negative 2 right here, which means I need to see a negative 1/2 out in front. And so now what I have is a negative 1/2 times the integral of u to the negative 1/2. And all of this is equal to my du value. Alright, so now we just need to add 1 to the exponent and divide by the new exponent. So that'll be u to the 1/2. If I divide by 1/2, it means I'm going to flip it over and multiply by 2 over 1. I still have this negative 1/2 out in front. And so those 2's will cancel. And what I get is a negative square root of 4 minus x squared plus c, but I'll just combine that with the other c value on the second integral. Alright, so we're adding all this stuff. I think what I'll do is I'll move that 3 to the outside. So I now have the integral of 1 over the square root of 4 minus x. This is supposed to have an exponent of 2. And then dx. So with inverse trig functions, one of the things I told you guys that's probably the most important is figure out what a is and figure out what the u value is going to be. So a is going to be the square root of this, which is 2. U will be the square root of this, which is just x. And then I want to make sure I know what u prime is because I need to see that in the numerator. And the derivative of x is just 1. So I'm going to write this as 3 times the integral of 1 over the square root of 2 squared minus x squared dx. So my a value is 2, my u value is x. I need to see the derivative of this up here, which I do. So this is all set and ready to go. So what I have is 3 times the arc sine. Remember, arc sine is the only one that doesn't have a 1 over a out in front. So arc sine of u over a, so that would be x over 2, and then plus c. So here is my final answer. Plus c. So just to make sure that things are working the way they're supposed to, we should be checking these each time with our graphing calculator. So go ahead and do that real quick. Punch this into the calculator, see what you get. Go ahead and hit the pause button while you do it. Alright, so I just did the same thing, and what I got for my answer was, starts off with 3 inverse sine, same as arc sine, of x over 2, and then minus the square root of 4 minus x squared. So we got that right. Alright, one more to try. So if anyone's looking at some of these integrals and just going, oh my gosh, this is hard, I can't remember anything, then my response would be to that is, what did you do last Thursday? Because last Thursday we had our review for exam 5 and 6. I just gave you guys the test. I said use it as a practice test. And we should have covered all of this stuff in that chapter. Okay? So we're just kind of going back to stuff that we learned and maybe pushing a few things, but trying to remember some of those strategies. If you didn't do that, you may want to take the time to do it. I have posted the the answers for that exam, so you can go back and look at those as well. They're on the sway page. All right, so when I look at this problem, to me this looks like a square root in the denominator where I've got a number minus some stuff. That almost sounds like an arc sine problem. And so I would set this up this way. I would start out by saying the integral of 1 over the square root of 1 minus, in parentheses, I've got x squared plus 4x, and we're going to put something else in here to complete the square. So I'm factoring that negative sign out of both of these terms, so it's got to be out in front. If I redistribute, I'll get what we had in the beginning. But now I just have to complete the square for that. You guys go ahead and try it. Alright, so to complete the square we would take half of this, which is 2. Square that, we would get 4. And then once I distribute this negative sign, that really becomes a negative 4. So I just subtracted 4 from the problem, which means out here I need to add 4. And so now what we have is the integral of 1 over the square root of 5 minus, if I factor this, I'll get x plus 2 times x plus 2. So I'll write that as x plus 2 squared, and then dx. And so now I think we're set up to do the arc sine. So my a value here is the square root of this number. I don't know what that is, so I'll just leave it as square root 5. My u value is going to be what's being squared here. So that's x plus 2. And then u prime, which I need to make sure I see in the numerator, is just 1. And I do see that, so we're set. So the answer to this problem is arc sine of u over a, so that would be x plus 2 over the square root of 5 plus c. Alright, I don't know why I feel like I'm off here, but I checked the last video and I think it was C8, so I guess we're on C9 now. Page 522, we're going to do 5 to 29 odd. Alright, that's it you guys. Have a good day. I'll see you on Thursday. Stay safe.